Welcome back to circles, everybody. We've already covered the basic definitions in circles and the tangent theorems having to do with right angles and congruent tangents to an external point. In the next couple of videos, we're going to talk about arcs and chords. Chords have a lot more theorems involved with them, so we'll be doing some more proofs with those. But let's talk a little bit more about arcs. They can get confusing because they have different ways of being measured. And whenever we create an arc, we actually create two arcs. So a couple preliminary definitions here. If we have circle C, that is, the center of the circle is C, then I can create what's called a central angle of circle C by using two radii. So with ACB, I have a central angle. There are a couple of different ways to define central angle. Generally, you'll see the second definition. It's just an angle where the vertex is the center of a circle. Now, just a little bit about the conventions dealing with central angles. Generally, when we talk about the central angle created by two radii, we're talking about the smaller angle. Of course, in creating one angle, we're always creating two, so this green reflex angle is also a central angle. But you'll notice when you're doing problems with these that usually we're referring to the smaller of the two angles. Let's say, for instance, that this central angle measures 50 degrees. Its reflex has to measure 310 degrees. So we've created two central angles here, one 50-degree angle and one 310-degree angle. Of course, this follows simply from the fact that all circles have 360 degrees in them. But we should be quick to remember that all of this space inside the circle, where we've drawn the angle, where we've measured these angles, even the center of the circle, none of these is a part of the circle. A and B both lie on the circle, because the circle is that set of points that are r units away from C, where r is just the length of the radius. So what we've really done in creating this central angle is divide the circle into two parts. We've created this blue portion and also this pink portion. Angle BCA has created two different portions of the circle where it intersects the circle at A and B. When we divide a circle up into pieces, each of those pieces is called an arc of the circle. So it's just a portion of the circumference of the circle. In the case we have here of a central angle of 50 degrees, clearly the portion of the circle between A and B that's blue is a smaller portion of that circumference than the pink portion. As a result, we refer to that smaller portion of the circle as a minor arc. But since every central angle divides a circle into two arcs, if we have a minor arc, we also have a major arc. So just to recap some of these terms, a central angle creates two portions of the circle, two arcs. In every case except for one, we have a minor arc and we have a major arc. When this happens, we say that BAC intercepts arc BA. And that's the notation we're going to use for arc BA. Just put an arc above BA rather than a segment symbol. Going in the other direction, we can say that arc BA subtends angle BAC. A couple of fancy words, but you'll definitely hear of them in the next few videos, so I thought I might introduce them now. So the only question left unanswered here is, what type of central angle does not create a minor and a major arc? Well, with a little bit of thought, I'm sure you can figure this one out on your own. But don't forget that it has to involve semicircles. Now, on to talking about how we measure arcs in circles, because we can actually measure them in two different ways, which can sometimes be a little bit confusing. Here in circle Q, we have central angle PQR. And we've divided circle Q up into two arcs, the minor arc, PR, but also the major arc, PR. Often, in order to distinguish between these two, you'll see that somebody puts an extra point on the major arc, so that we can actually rename the major arc, arc PSR. This is just an easy technique to help us not get confused about which of the arcs we're talking about when we've created a central angle in a circle. So let's say that that central angle, PQR, measures 150 degrees. Well, we can begin by asking ourselves the question, how much of the total angle measure of this circle is taken up by that central angle? That's some pretty easy arithmetic. We know that there are 360 total degrees in the circle, and we've taken up 150 of them with angle PQR. So we've taken up about 41 2/3% of all of the arc measure in the circle. That means that the remaining 58.33% is the reflex angle of PQR. This is actually very helpful to us because arc PR is going to be the same proportion of the circle as angle PQR is of the angular measure of the circle. So talking about that central angle actually tells us a lot about the measure of the arc itself. And in fact, that's one of the ways that we actually measure arcs. We can say that the measure of an arc is equal to the measure of the central angle that intercepts it. Now, once again, I want to make sure that you're aware of the notation here. Remember when we talked about the measures of angles, we use the lowercase m to denote measure. Well, in this case, when we're saying that the measure of the central angle also tells us about the measure of the arc itself, we're going to use the same lowercase m to tell us about the measure of arc PR, since the angle and the arc measure there are so closely related. Of course, as a result, the measure of arc PSR, the major arc that we created with our central angle, is 210 degrees. Now we can divide a circle up into as many arcs as we want, but of course it's always going to be the case that all of the arcs taken together are going to add up to measure 360 degrees. Otherwise we haven't taken account of the entire circle. Just as a quick and very poorly drawn example of that, we can divide up circle P into as many arcs as we want. In this case, 4 arcs. And those arcs are defined by the central angles that intercept them. So we can talk about arc QR as being intercepted by angle QPR. And let's say that's a right angle. Arc RS, which is intercepted by angle RPS, let's say that's 60 degrees. And arc ST, let's say that measures 30 degrees. Then if we wanted to find the measure of arc QT, that's just 360 minus everything that we've already gotten. And from there, it's pretty easy to see that arc QT is a semicircle. Hopefully that's clear based on the measure that you find for it. The other way to measure arcs has to do with their length, since they're just part of the circumference of a circle. If I create arc CE, it has a measure that's equal to the measure of the central angle CPE. And let's say that's 130 degrees. Well, that definitely tells us the portion of the circle that is taken up by arc CE. About 36% of the circle, but that's only one way that we can actually measure CE. Let's imagine that we were to take a string and place it along arc CE, along that part of the circumference of the circle. We could then stretch out that string and measure its length. That's another way to measure this arc. How long is the distance walking along the circle between the two endpoints of the arc? So what's the distance traveled from point E up to point C? Naturally, this is just called arc length. So when we speak about the measure of an arc, traditionally we mean the measure of the central angle. But there's another way to measure arcs as well, and that is by their length. But in order to know exactly what the length of an arc is, well, we need to know a little bit more about how big the circle actually is. And then we can use the information that we've already gleaned here about the portion of the circle that's being taken up by this arc and tell us exactly how long the arc is. For instance, let's say that the radius of this arc is 12 inches. Well, let's do a little calculation here to figure out how big the circumference of the circle actually is. As a reminder, the circumference of circle P is 2 times pi times the radius. Well, we already know the radius in this case. It was 12 inches. So 2 times 12 times pi gives us 24 pi. Certainly we can use our calculator to approximate pi and find a decimal approximation here. But 24 pi is the exact circumference of this circle, and often that's what we're going to be looking for, exact numbers. Just as when we simplify radicals to come up with an exact number, here we'll leave pi in place so we can have an exact number. Now we have the two pieces of information we actually need to find the length of arc CE. One, we know it's 36% about of the circumference of the circle. And two, we know the circumference of the circle is 24 pi inches. And since we're trying to find this distance along the circle between the endpoints, all we have to do is a little bit of multiplication here. 36% of 24 pi inches. Here's the important part where we introduce the notation again. The length of arc CE, I'll represent that with a cursive L. The length of arc CE is just that product. Let's use our calculators to find an approximation of what this actually ends up being. Well, we might as well find a better approximation of that 36%. Let's re-enter that into our calculator. So that 36% was really about 36.11, etc. %. That's helpful to us because we can now multiply that by the circumference. If you're looking for the pi key, it's right above the caret as the second function. So now we have our 36% of the circle. We're going to multiply that by the total circumference of the circle to get the portion of the circle that we're looking at, this particular length of this arc. I get about 27.23, if we want to round to the hundredths, inches. Let's write that down. So that 27.23 inches should be about 36% of the entire circumference of the circle. So we now have two ways to talk about this arc. We already know that the quote-unquote measure of the arc, which is the measure of its central angle, is 130 degrees. And just by calculating what portion of the circumference we're talking about, we've found that the length of that arc, the distance between C and E, if we were to keep walking along the arc, would be 27.23 inches. I'm going to leave those examples here. Next time we're going to talk about some proofs involving chords.